Welcome to another video. In this case, we're going to talk about some NMR techniques. We're going to look at aromatic coupling. We're first going to look at some typical values of what to expect when we see coupling in aromatic rings, and I'm going to walk through an example where we have a meta-substituted system like this. All right, so let's take a look at some typical coupling values that we're going to see in aromatic systems. So here I've shown a benzene ring, and I'm highlighting 4 different hydrogens on this system. And we're going to look at the relationship between these different hydrogens. Now between HA and HB we have an ortho relationship. So that ortho coupling that we're going to see is going to be typically about 6 to 9 hertz in magnitude. If we look at HA in relationship to HC, this is a meta relationship. So we have a J meta. And this is going to be typically 2 to 3 hertz in magnitude. And the last relationship we have here from HA to HD, this is a para relationship. So we have a J para coupling constant associated with that. And this is typically 0 to 1 hertz. In many cases, we won't even see that para coupling in the examples that we're going to look at. So let's walk through an example where we have a meta substitution. We'll apply some of these different things and see what the peaks are going to look like. All right, so here's our example. We have an X group and a Y group, and they have a meta relationship to each other. We're going to see what happens to the peaks that we're going to see for HA, HB, C, and D. So let's take a look at HA first. If we notice, HA has a meta relationship with 2 different other hydrogens. So the JAB coupling and the JAD coupling are both meta couplings. So if we try to take a look at what that peak is going to look like, we have our HA. Both of these are going to be about 2 to 3 hertz. So if we look at that signal that we're going to see this small splitting and then a second small splitting. These are the 2 meta couplings that we're going to see. If they happen to be exactly the same, then what we're going to see in our spectra is going to be a nice triplet, where once again we have this very small 2 to 3 hertz difference between the coupling value between those different peaks. This is going to be very similar to what we're going to see in the case of HC. HC also has 2 coupling values, but now these are ortho coupling values, so this is going to be 6 to 9 hertz in each of these examples. So if we contrast what we see for HA with HC, the peak for the splitting tree diagram for HC is going to have a larger coupling value and then another larger coupling value. Where now instead of having a 2 to 3 hertz difference, now we have a 6 to 9 hertz difference here. So in our spectra, this is still going to look like a triplet, but we have a much greater difference in our peaks, 6 to 9 hertz. So let's take a look at HB and HB, or HB and HD in the next segment. So if we look at HD, HD is an interesting case. This has 1 ortho value, and it also has 1 meta value. So we're going to have one coupling, which is going to be this larger 6 to 9 hertz, and we have another one that's going to be a smaller 2 to 3 hertz, but it also has a second meta value as well. So now there's 3 different couplings that we're going to see in this case. So if we try to construct the splitting tree diagram for HD, I'm going to start with the larger value first. So we have the 6 to 9 value first. And now we're going to add on to that 2 different smaller coupling values. And if we have a case where those smaller coupling values are exactly the same, then part of the splitting tree diagram is going to overlap. So if we look at the final spectra that we're going to see in this particular case, what we're going to see is a triplet for this portion and a triplet for this portion. But this is all just from that 1 proton from HD. So we're going to call this a doublet of triplets, or we can denote that a DT, doublet of triplets. Now HB is in a very similar situation. HB is going to have the ortho value between B and C. It has that same meta value between B and D, and a meta value from A and B. But for the sake of argument, let's say that this meta value is going to be different than this other meta value. Maybe this one is only this is coming up as 3 Hertz, but this one is only going to be about 2 Hertz. And let's see how that changes the outcome of our splitting tree diagram. So here we have our HB. I'm still going to do the large coupling value first. So I have my large 6-to-9 ortho coupling between B and C. Then I'm going to go to my next one, which we said was going to be about 3 Hertz. And then we have a smaller coupling value, the 2 Hertz coupling. So now this second meta coupling here isn't going to overlap. So now when we look at the final spectra that we have, it's going to look like a collection of singlets. In reality, what we have is a doublet of doublets of doublets. So we're going to denote that as a DDD, doublet of doublets. So hopefully this information gives you a step forward in trying to assign the different protons that we're going to see in these more complicated aromatic structures.